first agenda item is to do the labs. You must be here on time. We'll go through everyone for the labs. The first lab is going to be just you by yourself. The next lab after that, I believe we group you up. Yes. No. Yes. You'll be grouped up after that one. So you can find whatever pairs you like. But if we finish up everyone before you come in to demo yours, you will not get score. So keep that in mind. If you come in late, or if you come in after I've demoed everyone, you're not going to score.
Okay, cool. Bitmasking, for a reminder for those, is basically you want to when you have a register and you want to change selected for individual bits in it. You don't want to overwrite the whole thing, so you can't just say register equals to a new number. Because what happens is the number isn't just the number you introduce, like it's not just register equals 0, it's the entire register will be like 000 and the number that you want to assign. And those other bits in the register oftentimes correlate to other things that need to state that value. So you can use bitmasking to modify individual bits. For example, if you want to set a bit to 1, you use a bit set. Now in order to do this, the most common and generally the way that sets do it, we use a OR operator. So what happens is we have an OR operator that everyone remembers. So what happens when you have an unknown value and you OR it with a 0? The unknown value. Right, the unknown value. And when you OR it with a 1, what happens to the unknown value? Right, it becomes a 1. So that's how you set something. Kind of like back when you're doing something 124. Anyway, so moving on to here, we want to set this set in a register called reg. So they're doing reg equals reg or on the OX80 or 80. So translating each one that's it. It's storing the 1 and the rest is 0. Right. So they did it manually over there. I should have got ahead. I was supposed to 0. Anyway, what they did is they manually set the number to be only 1 as the 8th bit and the rest to be 0, so that when you OR it, you OR the 8th bit with a 1, and then the rest of it will be 0. So you set the 8th bit to 1. And doing the same thing for the 31st bit, so you can see they took the 31st bit, made it a 1 in hex, and then made the rest 0s. Much faster route that way than writing binary, so this is a fast way to do it instead. And they ORed it again, and they set that bit to 1. And here's the easier way, rather than having to kind of count it, you just shift that bit over to the 31st or whatever position you want to shift it to in order to set it, and you OR it with the register, and then that will set the corresponding bit to 1. And it does the same thing. It's easier to read, it's easier for you to do. Simplified even further, they're doing just reg or equals, kind of like this is just a shorthand version of it, so it's the same thing. Generally what you're going to be doing to set it is going to be written like that. And then cat, setting bits 21 and bit 23, you're ORing it with both the value shifted over to the 21st base and then the value shifted over to the 23rd base. And because it's only a single equal operator, it's considered a single write. So if you need both of them to be set to 1 at the same time, it won't mess anything up data-wise. And also just less write operation. That's if you want to set it to 1. Now you're going to obviously need to set to 0, so you're going to clear someone.
Any questions on setting like particular bits to certain values? This is just setting certain bits during the work.
You said that last one. I would only go with 1 at a time.
Yeah. So it's not really 1 at a time. It's more like when it does it as a single equals operator. So it's only a single write operation. Both the operations will happen and then be written into the register. But when you OR the 21st bit with a 1 and the rest is 0, because when you OR with 0, it's not going to affect anything. So all those values are the same. The 21st bit gets set to 1. Then it's ORing with the 23rd bit with a 1 and the rest is 0. So the bits that all the other bits, whether they be 1 or 0, aren't going to be affected. The 23rd bit is going to be set to 1. And then after that, it's written into the register. So now we're moving on to bit clear. Typically, we're using an AND operator because an unknown value AND with the 0. Anyone else? 0. Right. And unknown value AND with a 1 is right, the unknown value. 7, again, they're doing, well, I guess they're doing extra first. So instead of having just the bit that you want to be, here be the 1, it's the bit that you want to be here is the 0, the rest are 1, so they're unaffected. So we do reg and OX7F, which is 0, and then all the rest 1s, from 6 down to the 0 bit. So that doesn't affect any of those, and then you just set the 7 bit to 0. And then the same thing, just showing you how we did it again, except this time they're using the tilde operator. And some of you got confused by it on the earlier quiz, so just as a reminder, the tilde, what it does is, it's not the same as a not, where we'll just turn it to or a 0, or kind of like a coordinate. This one turns all 1s to, this one turns all 1s to 0s and all 0s to 1s, so it's flipped. So that would turn that OX8 0 into OX7F to make it the equivalent. But it's easier for you to read because you know which one's being set. The one that's the 1 there, the rest are 0s. So just to make it follow a format so you don't get up on things. And again, like they're showing you again, like we're trying to do bit 31, so following the same format with settings, we're just setting the 31st bit to the 1 and the rest 0, and then flipping it so that the 1s don't affect anything, and the 31st bit, which 1 splits, will be a 0, will clear the 30. You gonna follow so far? I'm kind of dry right now, but let's look at this not getting quick. The easier way, which is the way that almost everyone uses, no one does. You sometimes need to do that when you have to do multiple bits of things. When you want to do the easy way, you just shift something all the way to the 31st bit, then you want to flip it so that when you shift something, it has 0s at the end, and you flip it all into 1s, and that 1 at the end is 0, and then you clear that reg, that 31st bit usually, boom, done with that. So slide even further, you're doing the and equals rather than having to write the register twice, just because it knows it's going to be that register that you want to find. And then yeah, when you're resetting bits 21 and 23, you and you're nodding the entire thing because you have to write that anyway. And then you're doing it forward because, like I said, those are going to be unaffected. The first 24, you're doing 21st bit and the 23rd bit are going to be flipped. 0 for that last guy, the 21st guy, and then after that 0 for the 23rd guy. Single right operation, equal operation, single right. I'm good for that so far. Bit toggle. Honestly, me personally, I have to use it too much, but there are operations where you want to toggle bits, and to do that, you use the XOR operator, which is, if you use the truth table, you see that if you do an XOR value with an original value, it will be not up. Does everyone get what? Everyone remembers XOR, right? Like I said, I'm going to be covering basic stuff in the picture, so that's what I have to do stuff when I finish this class. Everyone good on the toggling bar? You go. That's the process. We good on the toggling bar?
No, not really.
Alright, cool. Bit check. Alright, so this one is a little bit more important because once you set a bit, you have to see that it actually, you don't need to do it every time, but sometimes a bit will be set by a different operation and you need to see what it is. Or it will have a default value or whatever, it will have a value that you need to see. So, basically, if you want to do reg and the bit to do the 7th bit, so you want to set the 7th bit check. The syntax is like so you do the AND operation because it's not changing it if there's no equal sign. It's just creating the value here saying that value is true. And for an if operator, if there's a 1 value in there, whether it be 18, whether it be a billion, it counts as true. And then, correct me if I'm wrong, the only way if becomes false is if there's a 0, right?
Correct.
Okay. Negative numbers become true?
Yes, it is. So anything, something that is faulty, so like a false input would be anything that's 0. Otherwise, all other values are true.
Right. So like I said, 13 to a trillion to whatever number, it's all true as long as it's not 0. So once that number is true, they're checking that bit there, does the same. Easier way though is while not. And was there an efficiency thing for that while you're doing it while not? Something? Or was that just thing for the one using check true only? So remember we said you wanted to try to do positive check.
I'm trying to remember why. There's a case where you needed to look at the universe, like if there's in one of the labs coming along, you weren't having to check for like the base is 0.
I mean, I have to do that, but I'm
not sure.
So that's not necessarily an easier way.
I don't think so, no. I don't know why.
Okay, yeah, that's good.
other thing, because sometimes the bit 0 is the bit to value you don't want it, and you have to wait until it is set. But again, it's situational. I don't know why. Alright, we're going to do another example in which one you wait until bit 9 is 0. Okay, yeah. So you wait until bit 9 is 0, you're saying while reg and one shift to the 9th position is 9 equals 0. Right, so you're making sure that bit is 0. The less crowded way to write that is you're just ANDing it at the ANDing the 9th bit to 1. And as long as the 9th bit is 0, that's going to return back to 0. So you won't do the while statement. Once it is a 1 at the 9th bit, I think that it's going to be a 1, but all non-zero values create a positive, so then it would exceed the well. Everyone good on that?
Yes. Actually, do you mind going back to the previous example? I'm a little confused on how that works.
Okay.
I was wondering if you could maybe write out how the comparison goes.
Talking about first data statement?
Yeah.
Okay. So, the red one behind you. So maybe.
You don't even have all points are basically
Smooth, okay. You can see that. If the reg at the 7th position, so let's give the reg an arbitrary value of we want to choose something. So we're saying like this, 1, and then don't care. Right? Should be this guy's going to be your right, right? And you want this guy, the 7th bit, or you want the 7th bit to be 1, right? And then we're shifting over this guy to the 7th bit position. So at the end of the day, this guy's going to look like this. This guy's reg. And this guy is going to look
I don't want to draw larger circuits. Reg is over.
you already know what you're going to do with these, but just zoom out. But this guy is going to be the reg. Alright, so this is going to be the reg value. So 1, and then a bunch of numbers. 3.
Those are all too small. You put the arbitrary numbers in there, so you can show them now.
Oh, okay, got it. And then 1, and then you don't care. Let's make them zeros.
Put some ones in there, because I think it really makes
Alright.
sense.
You know this. Alright. Everyone see that?
Yeah.
Alright, cool. So this is the register value, the arbitrary number. The one you really care about is this guy here. The one which should be the 7th position. Okay. So, what this guy becomes when you shift him over is he becomes 1, and there might be 0. So 1, 7, right? So then you add these two guys, so that becomes wait, these all okay. Because these are always going to be zeros if you shift it over, no matter what these guys are going to be. Tandem is going to be 0, right? 0, 0, 0, 0, 0, 0, 0, 0, 0. 1 is also 0, 0, 0. Right? So this is going to return back guy isn't 1, then this side let's make it 0.
Correct.
If you return 0, it's not going to do the thing. Once this bit becomes 0, this guy's a 1 and a 1, you get a 1, that's a non-zero value, just making sure you use it. Everyone got it so far? Okay.
So it's true if it's a non-zero.
Exactly, yeah.
I think I've noticed that there are some people who like decide to like shift it to the right. They're gonna make like a 1 or a 0, and that's a waste of an operation. You don't need to do that. That's a good check.
I want to wait until the 9 is 0. Okay, so rather than wait for the bit to be 1, we want to wait for the bit to be 0. What we're doing is we're shifting over the bit again, and we're doing it as long as it's not equal to 0. Reg and go. Wait for the 9 to be 0.
Wait for 9 to be 0, shift it over, and then make sure it's not equal to...
I know it's
Yeah, that's correct. Yeah.
So yeah. Does anyone have a question on it? It's basically the same thing classes like a week. Happens to work out.
Got GPIO example, LBC 17XX. This is your lab.
Yeah. Alright.
Actually, I will go over this. I'm not sure why this one comes up first. Actually, hold on. Hold on a little more.
It's because page 17 is
It shouldn't actually. Can you scroll it down, actually? Yeah. Okay, cool. I'll go into mine and we'll go back to this in a sec. Yeah. Okay. One thing to note, guys, this information, this is all those things that will end up on the mention. It's also something that you're going to use literally throughout the entire course. Bitmasking is just throughout it. There were so many times when, for one of the midterm questions, the reason why they missed a good portion of the points because of the fact that they tried to, because they're going to clear a bit using OR operator. And throughout all their capabilities use OR operators. I looked at the code like this. It can't ever really work if you need to clear this in order for them to work properly. So something to keep in mind is that there's a distinction between and ORs. Make sure you're able to do both. Don't hope that you can OR your way through everything. A lot of people find it too simple just to OR everything.
What's the main significance of bit masking? Like, what do you mean by masking?
So the idea of masking is the fact that you will basically mask out or ignore the rest of the bits. So a bit mask would be, let's say, it's a bit pattern that represents a couple of holes in it. So in the case of the AND operator, every time you have a 0 as a hole, that means you want to mask out all the other bits. You just want to let those ones fall out. Yeah. Okay. Yeah. Okay. So GPIO. Is anyone here who's never heard that term before? That's cool. Okay, so that's great. I'm pretty happy that everyone knows what GPIO is. Some people don't. And you should go over this area. Basically, they are your pins. They are your ability to take a pin and turn it high or low, or to turn it set as an input. You would read signals from it. You bring back to 124. That can be the case of your control signals you want to read off to see, okay, what state is this machine in? Or in other cases, you want to be able to generate control signals to turn to control a system. So either you're reading them in or taking them in, or you're outputting the control signals. The term GPIO stands for General Purpose Input Output, and that basically you can use them for whatever you like, as long as it's digital. One thing that I'll go into before we go any further is not only will we go over GPIO and how to use it, but also how to interface it with different components and think about how you can do so in such a fashion that will not end up destroying your hardware, making sure that you don't overcurrent any one of the pins.
So all you need to know in order to do this is bitmasking in C. We're wrapping on a breadboard if you want to buy reference, and then fundamentals of electricity such as Ohm's law, and how diodes work for the most part. Now here we have a little example of GPIO. So we can hardware to generate it. Using this is pretty much just a it's not a latch for the most part, it is a register. So we have a register here. We have a control signal that will indicate what the output should be. Actually, this is more for flowing high club. You will have one control signal internally to your board. That'll be the direction. If the direction is low, that means you are then outputting in signalizer. If it is high in the signature, that means you're taking the signal in. This is how this architecture is set up. Your pin can be used to either read values or output values. The same registers you'll use to be able to send a value out to the pin, and the same register you'll use to also read the pin out. A lot of different designs will end up, a lot of different microcontrollers will end up having a pull or pull down register capability. For example, the LPC 1756, which is the board you guys use, defaults all the pins to pull up, and also to input. Now, I'll ask you guys this question. Why does it seem like the safer bet to set up all your pins as inputs, and also like pull up? So there's two separate things, so one is input and then one why we pull up.
Maybe set it as input so that when you connect something you maybe shouldn't have, it doesn't supply it voltage to the current that's not expected.
And then what would be the result if we did apply something that was current that was expected?
You could mess up the part.
You could break the part, and you could also probably break your own controller as well.
Yeah.
We need something like something as input. In fact, to your 124 last voltage. What characteristic does that thing have?
I think it thinks current.
Yeah?
It thinks current.
When it's input?
I don't think I remember.
Not exactly. So more technically, you could have leakage current going in or out of the device, but in this case, it should very much miss, which is kind of a hint.
High impedance.
High impedance. That's correct. When you're input, it's almost like you're not even connected. It's like a very large resistor at that point. So if some other signal on that particular pin is going to line high and low, it will not affect those. It will not affect those pins for the most part, unless you have drastically high voltages or drastically negative voltages. That gets into contact emissions for this device. For the most part, it should be high impedance. Therefore, very little to no current will flow in or out of the GPIO when it does input. Now, why do you think that it might be useful to pull it up? I guess before I go to that is, what are the three states that a pin could be in? So what's it?
High low.
So high, low, or high peak. And for the most part, you can set up a wire with a pretty large resistive pull up. And it would for the most part be high impedance, but there'll be a little bit of a flow through that resistor or out of the resistor. So now, why would that be useful for a device?
Well, I mean, like with your bidirectional buffer right there, like you wouldn't want input going into the side that is currently going as output. So for anything that would like hypothetically provide input to a device, you want to high B it when it shouldn't be.
No, I mean, it's fine. Those other buffers are perfectly fine. And, having pulled up or pulled down or high B doesn't really affect it much. Here's another question. What happens? Okay, so we have three options. I said one for the pull up. You probably make an argument for the pull down. Would you want it to be high B? Someone from the corners. How about you?
I mean, I guess you would want it to be high that way, like nothing really like goes input. Yeah.
Okay. So now I'm gonna bring this over to some people who are actually advancing now, or maybe took formula or did one of those things, or kind of built a project. Let's say you have a motor controller or a controller that you're putting signals to, and by default you left it to be high Z. What could you expect out of that? What do you expect to happen with that board, that setup?
It happens what, the components or the
Yeah.
if I left the 10 high Z, that's when I expect really anything going on with those components.
It could be either on or off, depending whatever is external like reference line.
To be on or off.
Yeah.
So I turned on my robot, and the signals to the motor controller are going between on and off. Is that okay? Why is that? Okay, let's visualize what would happen with that system. I got like a little tank robot, it's got like a couple motors, and I left it on in high Z. What could end up happening there?
The motors wouldn't function as intended for sure. I mean, it sounds like you're like PWMing an input, if anything, if it's like high Z.
Thank you. So when we go into each one of these assignments, I want you guys to think about what you would do with this in real life. So let's say you're talking to some RAM or to a sensor or to a motor controller or what have you. These are things you have to think about, like, what should be the default state of your pins when it turns on? Because if you don't know, let's say it is floating and there's no pull up or pull down, it can all fit between the two. I've had robot setups where like you literally see the motor jittering back and forth because the pins are fluctuating between high and low. And the motor controller knows what we'll do about that. We could have added our own pull down resistors, or we could have used the built-in pull up or pull down resistors on the controller. So there actually is no difference between the desire to pull them up or down. I'd actually say usually pulling it high and just reducing the amount of current that flows. But the point of actually setting them high or low by default is so that you know there's a defined state for each one of the pins. That make sense? You get it? Alrighty. So that's another part of the architecture of a pull-up of a GPIO. Typically they will have the ability to become in or output. They will also have the ability to be pulled up or pulled low. There's one other thing, and this is usually a safety feature. This little circuit right here. Can anyone explain to me what in the world is happening here?
Well, it looks like you're blocking VCC from flowing altogether.
Sure. Yeah.
And then you're locked ground.
So it's I feel like it's accounting for like the GPIO pin being high or something like that, so the rest of the circuit doesn't get affected.
Actually, definitely. Let's think outside of the box, and particularly let's think outside of what's kind of right here. So think about the GPIO itself. Think about what's happening to it on the other side.
On the other side of this circuit.
Yep. This is on that side. Excuse me, name of the red jacket.
Yeah. Yeah.
Yeah.
Yeah.
GM?
Yeah.
What do diodes do? What's like their one main function?
Control the direction of the current.
Cool. So it allows current to go one direction but not the other, right?
Yeah.
Awesome. Alright, so what indicates what direction the current flow?
The triangle.
So current can only flow in this direction, right?
Yeah.
And then only up this way?
Yeah.
Okay, so take a quick little look at this and think about what values you have in that would make it useful to have these diodes here.
The GPIO is 0. You can't apply current to pull the line up.
Get you a little more. You're getting there. So I could have just removed these and I wouldn't have to hit it.
Does that whole,
Does it sound like a pull up and a pull down resistor at the same time?
No.
that whole, yeah, that whole blueprint. Okay. Alright, so I'll give you guys one half of this, and then you guys should be able to solve the other half. A diode only allows current to flow when the potential at the triangular bit of the diode is a lower potential than the opposite side, correct? So at this point here, you have 0 volts of no potential. What is the only way in which current can ever flow from this point to this point to the GPIO? The voltage is going to be
Negative voltage.
negative voltage. Okay. A negative voltage flux going over to this circuitry might be what?
Let's stuff up.
Let's step up. Guys got that? So, in order to protect the GPIO, we call these ESD diodes. So we make this GPIO ever pull lower than 0. Current, besides pulling current from these points out and from these components out, you would pull current from the lowest resistance source, which would be through this point here. Y'all get that?
Yeah.
Cool. Now tell me what the purpose of this guy is for.
Do you ever get something higher than GPIO?
Right? Yes. The only way for current to flow in this direction is if whatever you have here is greater than the value here. So if you ever have too high of a voltage, that will clamp it down. It'll pour current up through the BTC. And I think that's okay, well then it's damaging the rest of your components. It could, but as long as it's a short burst of high voltage, like for example, when you touch things. If you're ever working with the SJSU board, in SPE, if you just touch the metal part of the bench, the little white part, that will discharge you. You can also touch like the power slice like that, or you just want to touch the metal to discharge yourself. Because every time you touch the board, you're usually injecting electrostatic discharge into it. Could potentially break it. Haven't had any problems thus far. I see people like, I think one person put theirs inside a sock. And that's probably didn't break. But I mean, I see people put them in a whole bunch of different areas. It was a big sock, kind of like a stocking, but not exactly. And I thought it would be cool to put their board in there.
I feel like that makes it worse.
No, it does. No, it doesn't help. I told them that might not be the best way to do it. Like, yeah, I took with how to live. I'm like, alright, $80. Alright, so that's the construction of a GPIO. Any questions? Also, one little thing that would be probably good for you guys to look up, so you guys know, maybe you guys get thrown this in the interview. This symbol here is called represents a Schmidt trigger. Maybe Dr. Bindle went over this in 110, but yeah, if you don't remember it, look up Schmidt triggers. They're pretty interesting. Now to some hardware coding. Yeah, they cut off. Let's see if I can pronounce it. The Zoom team actually like. Oh yeah, this is okay. I'll scroll over. So we have a couple of registers that you'll see inside of the data sheet. You'll have FIO direction, FIO pin, FIO set, and FIO clear. This one represents, if you might, actually, let me ask you guys, what do you guys think this one represents? Direction. Okay, you guys stop talking. So we get someone who's back in that area, so that's what you guys think this one's for. All the way in the left most. What do you think? Okay, and then this one? Okay, and then, what do you think? It'll be right second. You say what? Wing check. Okay. What do you think this particular register is for? Yeah. Whenever you can get it. Cool. That's pretty much the whole point of everything that's over here. If you put a 1 in the direction position, it should actually be the output for a 1. Yeah. If you put a 1 in any one of the bits inside of the direction of register, that one's an output. If you read back a 1 from any one of the pins, that means it's high. If you read back a 0, low. If you write a 1 to this, it'll be 3.3 volts for the SJSU board. Write 0 volts. The cool thing about these registers here is that they allow you to basically set or clear without having to, all you have to do is put a 1 there in that fixed position, and it'll go and clear the corresponding bit in the corresponding pin. So they will clear. You can write only read from them, you can write to them, and they'll do all the work for you on your behalf. For the most part, you can use these. I'd say just work with FIO pins to get more experience in using the AND and OR operations. Because you're going to lose the ability, like most other registers do not have a set to clear register for you. Okay. Yes.
So, like in 1.7, we would just use the API to call to still set one of these pins higher and low. So, are you saying that for like one of these like labs that's coming up, we're going to have to use these ports to actually change it ourselves manually?
Yes, correct.
So, could you show us an example, maybe, like how it's supposed to do that?
Yeah, sure. Might as well go over to you.
Yeah.
So let's set. Okay, so here's the API. I want you to configure the rest stuff over there. What I want you to do, I want you to make port 2.9. That one's going to be your input. Okay, so you want it to be your input. And then I want you to also configure what it does as output. That'll be 0.27. And I also want you to set that one high. Okay?
Okay, so typically when I approach this background, remember how we did bitmasking and I said reg equals whatever? These guys are going to go to the registers that you're using. These reg. And when doing this, I normally look at the data sheet, but half the answers are right. We do LTC, right? And if you guys don't know how to look stuff, I'll show you how to look up. GPIO, and then we want to do port 2 pin 9, so we're going to do GPIO 2, right? We want to set input, so we use the register that's the input register, which is the FIO direction. That's one right there. Here. And it says input, we need to set as a 1, so you guys remember how we do that.
So, just so you guys know, the bit position is mapped to the pin in that port. So, when we see, if you look a little closer, LPC GPIO 2, that is port 2, all GPIOs in port 2, and then 9 is the 9th bit.
Moving on to the output for 7, very similar, line code obviously. GPIO, and then we're doing port 0. You are still setting a direction, so using the directional register. And we need it to be 0 complement. Not so the 1 step, 7. Then we need to set, what's it called? We need to set the same pin, I believe, to be by highlight, alpha highlight. And then setting the direction, and we need to set with the FIO set register. That's probably the easier way to do it. Again, it's the same port. Okay, that's fine.
So, can I get it from that example?
Pretty sure.
When you say port, I feel like the whole cluster is like P0. So those are the like that port refers to the whole cluster, and
So this particular board, there are multiple versions that have more and more pins, and we have one of the ones that has the probably least amount of pins. So just to give you some idea, the reason why there's even multiple ports because everything in this, all the registers are mapped to around 32 bits. All of them. We actually cannot access anything less than that. So every single register has up to 32 bits. So if we want to have, let's say, 64 pins in total, we need to separate them over two registers. So we have port 0, which is all the pins that are underneath the port 0, and so forth. This one our board should be able to go up to, actually technically up to port 4, but there are many pins in port 2 and in port 1 that don't really zip on the board. So. Also, one little thing. Anyone see the error with this code? Yeah.
You said that it had an input or output?
Yeah. That over?
We said the input 2.9 and then the other one was output 0.7. And you have the issue to make it an input or an output?
Oh, that's what he's trying to do with the first two lines.
Oh, that's their input output.
Yeah.
Which part is the input output?
Direction.
Yeah, higher direction, whether or not the input direction, the output direction, so if I are zero.
Okay.
Yes.
So if you're doing output, it should be just the low instead of the high, and then the opposite thing again for the output.
Correct. That is correct. Yeah. So to quickly change that over, that would simply be tilde ampersand or that. Boom. Answer your question?
Yes. Cool. Actually, one more question.
Yes, you said.
So those names, LPC, GPIO, 2, those are built in.
Correct.
Yeah. Do we ever go any lower than that?
I showed an example of that last week where we had like a bare register and we had a pointer to it and then we just used it that way. But for the most part, that value, that name, is just an alias, so like a name for that address position.
Oh, okay.
So that one I believe turns into, LBC GPIO 0 turns into like hex 2009 and then like, I think C1000. I forget what the exact number is. Basically, that's a big map. But that's just really being like a literal address. Alrighty. Now off the switch. So here we're going to be interfacing a switch, let's say it's on port 0.pin 2. The whole thing? Yeah, that's the whole thing. Cool. Awesome. It's a very basic schematic. That's a little tactile switch. It's either disconnected when it's not pushed or it's connected. I'll ask this question, another EE-like question. What is the point of this resistor here?
Pull down resistor?
It is a pull-down resistor. But what happens if, like, okay, so let's just put this guy down here and it's connected directly, and then I remove this resistor.
We would have no, like, reason to go to ground.
No reason to go to ground?
Well, did you remove both resistors?
Yeah, I can move both resistors.
GPIO would always do that.
Okay, and then what happens when I hit the switch?
It would still be zero.
Yeah.
But you short your supply.
There, yeah. Make sure your supply. So you need a resistor there to make sure that you don't destroy your supply. Yeah, yes. Then what about the inline resistor here? So let's say we got this guy in. So before we had a direct connection to this point here. What's the point of having this resistor here? And no one on this side, except for maybe you two back here. How about someone else? After this one?
You said what's the point of R3?
Yep, point of R3. Okay, don't say nothing then. Alright, what about you? Any ideas?
we already keep them let's take out the pull up.
Oh no, keep both. So you have both. What's the purpose of having the R3? So we can think about the system as what else when you remove it, what could be the dangers of doing so?
Might it have the same story as shorting out the PCCs, but instead it's for the GPIO?
Okay, so how can you sort that out? What's the situation?
Like if you remove R3.
Oh, well, if you remove R3, there's no way to sort it out. And you have to give more information to prove that it's been sorted out. So in what situation would you sort out PCC?
Like maybe if it has a lower potential than what's going from the GPIO?
So if the GPIO has a lower potential,
No, like higher.
higher potential, then what specifically? Like, so higher potential relative to what? Higher potential is the DPC.
Yeah.
If that was the case, that still doesn't do anything, still have to give one more bit of information. Some more information about the state of the system. Like y'all probably should answer this. And then yes.
It's current limiting, right?
Yes, it is current limiting. In what situation would it help current limit?
Well, what if your supply is providing more current than your GPIO input?
That's a good one. Yes, that's actually a good one. Although I chose 1K because I knew it wouldn't have that issue. So assume that the 1K provides that protection. So if I removed it and kept it up, what could be the case in which the GPIO can break? Because for the most part, if the GPIO is, well, I don't want to give out too much information because there are 2 bits of information about this system, and if one is in one state and the one is in another state, it causes destruction. In all the states, it should be fine for the most part.
The switch is engaged and the GPIO is output.
Correct. Oh, actually, one other bit of information. What does the GPIO outputting?
Higher than PCC.
No. Let's say we can't. What would be the option? 0. Correct.
Why?
I remove the resistor. I test this up. This is VCC. This is ground.
Yeah.
So short circuit to VCC.
Yeah.
Same situation as if you remove the tank. That's the reason why we have the. That's the reason why we have the inline resistor as well as the pull down resistor. If you were to ever accidentally set the pin as an output and then pull it low in this configuration, and the button was ever switched, you would destroy your board. That's the purpose of that. Now, you say you're being safe. You can omit it if you wanted to. If you're trying to save costs, I would probably omit them. Not for the next SJSU board though, because I know people will break them anyway. But if you're trying to really cut costs, keep and remove as many resistors as possible, that'd be one of the things you might want to niche. If you know, as long as you know your firmware short. That's all hand on. Yeah, that's the switch. Schematic. Yes.
Is this internal to the board, or is it?
No, this is external. Good question. Let me go check to make sure that the thing is not okay.
Alrighty, we are live.
Okay. Let's see. Okay, so actually, Jack actually asked a really good question. The question was, do all the ports 0 through whatever end up doing the same thing? Is the other thing functionality? Or do they have a difference between functionality? And the answer to that is, for now, they're all just GPIO. They're all just more pins, they just have to be in different registers. But as we go further, you'll find out that some of them can be used as UART pins. You don't know what that is, don't worry, it's not a communication protocol. Some of them can be used as SPI. Some of them can be used for like quadrature encoders. You don't know what that is, it's fine. Motor control, so on and so forth. So all actually have extended functionality, and usually you can must change them around. So that'll be happening in the next lecture. After this, we'll go into how do you go about switching the functionality of a particular pin. And yeah, so for the most part, if we're doing GPIO, yeah, most of them can be GPIO. There are some systems that dedicated pins can only access inputs, some dedicated pins can only access outputs, and that's how the hardware ends up coming. Any other questions? Yeah. Cool. Well, here's a little example of how you set them up.
This is a week, right?
Yeah, do it next week, yeah.
One last.
2 labs.
But one of them is just back to state built it, right?
Yes. Well, actually, there's 3 labs. One of the stuff is built it, the other one is showing that they can do the AEDs. For the most part, I'll actually,
That's right.
for the most part, actually, I won't even go over that one. If you have to submit it, that's all I'm looking for.
So what is the due by? Midnight?
It's due before class starts next week, Tuesday.
Okay, we submitted and we demoed live.
Yes, correct. So here we're going to interface with an LED. So 2 configurations here. We have the active high and the active low configuration. So in one case over here, we have the active high configuration. If you pull the pin high, you'll source current through this path here to ground. If you pull it low, the potential here will be the same, therefore no current will flow. In this situation here, if you make this pin high, there will be no potential difference between these points, therefore no current can flow. If you make this low, then current can flow through this path. Pretty simple. This isn't really well. There are a lot of cases where you would end up wanting to put the configuration in active low. I won't say this is a very special way about this, but let's say you have you want to get a certain brightness. Let's say that the resistor is immutable, it has to be that value. Well, maybe you're able to change the VCC or the value that you have for your for the current going through the particular circuit. There are a lot of times when you can sync more current than you can source. PTLs actually have that issue. Look at their output stages. You can actually see that there's a lot of different things that block and can drop voltage coming out. So pulling it to ground is usually you can sync more current than source. In that particular situation, you would then want to do this configuration because you can get you don't have to worry about voltage drops on the output. Most likely it'll be as low, very close to ground. Whereas on PTL devices, even though you power up 5 volts, you might get 2.7 to 3.3 volts. Whereas at ground, if you set the VCC to 5 volts and you pull that thing to ground, you get the full current range of just 5 volts through that particular diode. This one will take into that. Obviously, we're working with the CMOS, so we don't have to worry about that particular issue. And I remember in the data sheet, in the electrical data sheet, that the sink and source currents are around the same, but that's not always consistent. I've seen some single board computers that end up being they can sync more current than they can source. Yeah, sync more current than they can source. A little negative information for you guys. And then we also have a little bit of information here on how to do that. Similar to what we had over there, set it up as an output, then you turn it high or turn it low, depending on what you want to do. So, and that ends up being the end of GPIO. Are there any last questions about GPIO and how it works?
Can you repeat what you were saying about this part again?
You mean thinking more, or just going over the configurations?
The configuration.
Yeah. With this configuration where you have GPIO at this point in the schematic, or this point in the circuit, in what configuration can this end up, in what configuration can this light up this LED?
When it has a high potential.
Yes, so what configuration for GPIO would that be? It would have to be a what? Sure, okay, so we set it high, but what do we have to do in order to make sure it actually becomes high? What are the things we have to set? So if I have a pin that's an input and I try to set it high, would anything happen?
Oh,
Correct, yes. So let's see output, and let's see high. You put output in low, it should, correct? And then that configuration over there, how do you get the LEDs turn on? GPIO has to be what?
low.
And then, so it has to be low, and then what configuration do you do? Input? So what's one of the things you said about inputs in 124? What are they? What's one attribute of them? The high impedance. Therefore, it says if you have P2E, like whatever, let's say like 300 ohms here, then you have a million ohms here. Very little current will flow through there. We want to turn this LED on. So what does this need to be in order to allow current to flow? That's right. Low and output. You understand? So if you want to hold it to 0 volts, if you want to actually control the pin state, either high or low, you need to be in output. No ifs, ands, or buts about it. If you want to just simply read the state without pulling the line high or low, you want some other circuit to control that. It must be an input. Make sense? One thing you can do is you can keep it as output, you can still read from it. That's just saying like what you set it to last. So, keep that in mind. Yes.
So internally in the GPIO pin, if it's an output and it's low, does that mean that it's connected to ground?
Correct. If it's input and you read low, that means some other source is connected to ground. If you read it and it's high, 3.3 volts or whatever constitutes a V input high. Cool. Alright. Now to get to the assignments. Pretty simple. It combines some stuff from last week, doing tasks, as well as using the GPIO. It should be quite simple. There's a couple parts of this. So the objective for this assignment is for you to be able to manipulate the microcontroller's registers in order to control a pin's state. For example, setting it up as input or output, and then setting it as high or low, or reading it as high or low. We also want you to use this to be able to sense input signals and be able to control LEDs. But on top of this, we also want you guys to actually build a driver. Now here's an API that we've developed for you guys to work with. Here, yes, implement all class methods specified. All methods must function as and work as expected with their method names. We have a lot of notes in here. So just so you guys know, this is how this conference is going to go by. We're going to give you a bunch of stuff in the beginning, kind of guide you through, handhold you a little bit, but then little by little, every week we're going to start moving more and more away from you. Until eventually one of the last drivers you have to do is completely empty. And you have to implement everything there. And I already have an idea of what functionality is going to be necessary in order to make the lab work. So for each one of those, you should make sure there's a designated method for it. The better you design these, and the more you test your code, the easier it makes doing the application part of this. Because there are two parts, driver and application. So here's the driver. So set as input, set as output, set direction, set high, set low, set get level, and those pretty much what they do. And Instructor is also using instructions. But for the applications, you will create two tasks. You'll create two tasks. You will have a task that will you have two tasks that will control, one that will read from an internal button and manipulate an internal LED. You have another setup where you'll use and generate one of those schematics circuits that we showed, and have an external button and an external LED. You need to be able to, whenever you press the button, it should turn on the LED. When you release the button, it should turn off the LED. Same thing for the internal, same thing for the external. Oh, yes.
So can you define internal and external LEDs?
Yes. Sorry about that. We should do that. The better word for that would have been on board. So the LEDs that are on board your board, if you plug it in, you'll see them light up all red by default. Here's a good example of that here. And see the board. Yeah. So here we have a board. All the LEDs on the bottom here are lit up. So when you press this button, or any one of the buttons, doesn't really matter which one you choose, it should light up the corresponding LED right above it, or whatever LED you like. Then you'll use the expansion bus on this side. Use the expansion bus in order to control and read from an external switch, and to control an external LED. Building the schematic, building the circuit that we showed in the GPIO lecture portion. So a couple tasks here. Might be useful to actually use the parameter here. That's a little hint, not much. Yes.
For the external LED, is there any specific components that you want to use?
use Redword if you like. I have no. If you come in here with like something wire wrapped, if you come in here with something soldered, if you come in here with like with a Redword, that's fine. Even if you come in here with like jumper wire hanging off it, that's fine. But I would recommend you have a more stable configuration because I've seen people like something happens, something gets pulled, I can't get that thing to work. Like, oh, it was working like downstairs. I'm like, yeah, it's gotta work here. So, little things that help you out a lot. I usually give around 5 minutes for you guys to get set up in the room. So we'll come in here, I'll give 5 minutes for you guys to get your lab ready, and then I'll go through. So it's not like immediately.
Do you have an external switch from 127 there? I don't remember if that's the component.
I don't believe so, but you should have them from 124 if you have those little kits.
Is there?
Yeah, you had a couple buttons there. Oh, actually, you know what? I am wrong. No, you do not. You have the little flippy switch. You have the little big switch. Yeah. I don't SJSU. You can find it from there.
Crap.
Yeah.
You got your E98 project, you got a bunch of them right there.
Also, you guys need a component for excruciatingly cheap. There is Estell Solutions. It is near the park and ride. You can find LEDs, transistors, old TCL, PMOS chips, capacitors, everything you need, all base components. No composite components for the most part. They're like DC converters in there, but I don't always trust those things in there. Be careful what you get in there. Bring a tester if you can into Estell Solutions. So some of the requirements here is that you must not use the pre-existing GPIO class, but you may actually going to need to use the LPC17xx.h file. It's a library, it's a list of register mappings. You're going to use that to generate your driver. So you must use 2 tasks above. You must pass a parameter to these tasks to inform them which switch or LED they're reading or controlling. So some way you should pass any information to these tasks and tell them, yeah, I want you to work with this port and this pin, and yeah, you want to make sure you do something like that. There will be a read switch task as well as a feed control LED task. The idea here is that you should only have to create. You want your code to be generic. You want to make sure you have code reuse. That's the big thing here. You want to make sure you only have to write two tasks. One that reads a switch and one that controls an LED. You should be able to tell them, say, hey, I want you to work with these different variables here. You know, this switch will control this thing and send this information here. You can pass that in however you like. Make a structure, embed it into the 32 bits that you have with the function pointer. However you like to go about it. One other thing here. If the button is with, so here's another thing that I add on to this, giving a little bit more complexity to the design. I said press before, and I thought someone had talked to me about that. It's like, it's too difficult, we gotta make it easier, but for the most part, it seems like it's still here. Don't do it on the press action, you can do it on the release action. So basically what you're looking for is a falling edge, or rising depending on what the clarity of the input could be. Just write a little bit of code to figure out the state at the point where the pin is, the switch is released. When the switch is released, then you change the pin. You press and release again, you should toggle it. That's kind of the actions you want to have happen with the LED. So in total, you will end up creating, and that's what I mean by this, is using a task create, 4 tasks, 2 of the research tasks and 2 of the control tasks. Pass in parameters to change the behavior of each task. You see the block 2. What is this? Block 2. I think that's here. Yeah, block 2. Upload all relevant CPD files into Canvas, but what I mean by that is put them into a PDF form and then upload that. No need to include like LPC headers like that. It needs the code that you worked on. And if you made any additional like library files like lab, GPIO, HTTP, lab, CDP, you want to include those in there as well. And find the full rubric and breakdown. It will be on Canvas. it'll tell you like 10 points for doing this, blah blah doing this. Those are your requirements. Please read them and make sure that whatever you design for conforms to that. If you go willy-nilly, like for the most part, if you do this entire thing here, you'll be fine. But you might have missed a particular nuance about how I see the rubric to know you have to have this blah 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 happen. It's almost exactly what to take note here. But that can kind of give you an idea of what you do first, what's the easiest, and then attack that first. So for example, making tasks and having to communicate with each other is really easy. I'll give you points if you have tasks and they're communicating in some way, shape, or form. You got the LEDs working, but you get the tasks working because the tasks are less points, go for that. So think about what adds the most, think about two areas. What adds the most value to your grade. Similar context to when you go to a company, what adds the most value to whatever you can work on. So keep that in mind. This is a value thing. You have to be able to prioritize yourself. Try to get everything. If you can't get all the points. And for this assignment, you really get all the points. But if you can't, for whatever reason, get as many points as you possibly can. Yes?
So this assignment is basically just use this switch on the board to light up a light on the board and light up an external diode.
Yep.
It's basically
Yep. External buttons is on the external LED. Internal buttons is on the internal LED.
Oh, external button.
Yeah.
External button.
Also, extra credit. Be able to put like a weird button combination in there or whatever you like. Just do something fancy with something flashy. I had one person do like this really cool animation with the LEDs when you do a certain combination. You have to get extra credit. Another form of extra credit too. So there's two parts of extra credit. If you want to take an L on another assignment, it's my fault. Look at the other assignment, see how many points you can get, and then kind of map it out from there. But make a class that is generic that can be used with both port 1 or port 2. As it stands right now, let me see. Okay, no, there are quite a few port 1. So the buttons and LEDs are all on port 1. So you can do this entire assignment on port 1. But there are quite a few other pins like port 0 and port 2 that are on the expansion port as well. If you can get your driver to work with it's not really cool. Yeah, you can't do that. But for the most part, be able to handle multiple ports with a single class. Do that to get some more extra credit. Any questions?
How many lines of code can we expect to write?
Depends on how you code. But honestly, there are probably more lines for the amount of code that you end up writing. There are more lines in comments and in code from up here than there are lines that you'll probably end up writing. If you write your code, there's a way you can write your code in such a way that's so clean that it should be able to be one-liners for most of the stuff. And reasonable one-liners, not like the eccentric, like trying to keep everything with multiple semicolons like that. Like a typical one-liner. And then down here, the code shouldn't be too gross. It should be more additions of code. So it shouldn't be that many lines of code. I think the biggest thing will be figuring out the biggest thing is usually trying to get your hardware to act the way you want it to act. Yes.
Where would we find which ports go to which switch and which onboard LED?
Yes. Great. I can't believe I didn't go over that. Sorry about that, guys. Yep. Let's do this. I think you should have two. Oh, it's a shove stack. That's not what I want to go. Here I am. Oh, we're pressing the wrong button. No, I don't think it's wrong. Okay, so from the folder, you will look into references. From here, you will find SJSU PCB layouts. You'll find quite a few other revisions of the schematics. You want to look for revision 4. I think almost everyone has revision 4 board. I don't know what happened to revision 3. you'll have the PDF here. Let me open this up. We have this entire schematic here. Right here you'll see the LPC 1758. You can see all the separate pins here. So port 1, pin 0, and so on and so forth. So we can also embed information about what these other pins can be. For example, port 118 can be a USB indicator for activity. This one right here can be a PWM capture, so you can see how long the pulse has been. This one can be a physical M, and so on and so forth. If you look out to the sides here, there's usually some notes on the connections. For example, this one will say that this is part of the port 1 connections. You'll see that this one actually connects up to IR data. And for our LNE specifically, you want to look at these two pins here. So we'll see that, okay, LNE 0 is port 1, pin 0, and then so on and so forth down the line, so 1, 14. And then the switches will be 9, 10, 14, 15. And those will be your switching pins. You can turn those up to input or output. Another bit of information that's really useful here is these little bit of text here. It tells you which section of the dash to look into. Because it represents page 2, column 3, row A. So if you look over at page 2, and you see up here, you'll see like this stuff up here. You'll see column 3, so it starts at 1, 2, and 3, and you'll see section A. You can see how it goes from here to here, and that's where the pin connection happens. And it also references where it's all connected elsewhere. In this case, page 1, 5A. That's how you kind of get your way around this. And you can also see the other devices on here, like there's a flash memory, there's an accelerometer, there's a couple switches here as well. And this will be your route for figuring out what pin is connected to what and how to go. I think that's what we're going to show. Any questions? Cool. All right. We're getting out early today. You guys can have a good rest of the evening. If you guys are having any problems with SJSU dev environment, I did make a push. Yes, Jeff.
Oh, no, not pushing. I want you to listen.
Okay. I'll stick around so you guys can help. If you're using a Mac, I actually made an update to make sure that if you have like another version of Python following the machine, that it reaches the right version of Python. I'll push that out pretty soon. I'll make an announcement with that push. Should hopefully work with everyone. I had someone else test it, but yeah. Otherwise, you guys are dismissed. You guys ready to go? Kind of. So I just actually does one, and then I branched out into SJSU. I kind of revamped a lot of things. So SJSU doesn't have a lot of these issues. And I'm trying to back propagate those solutions.